Now that we've seen what a derivative means and what it has to do with rates of change, our next step is to learn how to actually compute these guys. As in, if I give you some kind of function with an explicit formula, you'd want to be able to find what the formula for its derivative is. Maybe it's obvious, but I think it's worth stating explicitly why this is an important thing to be able to do. Why much of a calculus student's time ends up going towards grappling with derivatives of abstract functions rather than thinking about concrete rate of change problems. It's because a lot of real-world phenomena, the sort of things that we want to use calculus to analyze, are modeled using polynomials, trigonometric functions, exponentials, and other pure functions like that. So if you build up some fluency with the ideas of rates of change for those kinds of pure abstract functions, it gives you a language to more readily talk about the rates at which things change in concrete situations that you might be using calculus to model. But it is way too easy for this process to feel like just memorizing a list of rules. And if that happens, if you get that feeling, it's also easy to lose sight of the fact that derivatives are fundamentally about just looking at tiny changes to some quantity and how that relates to a resulting tiny change in another quantity. So in this video and in the next one, my aim is to show you how you can think about a few of these rules intuitively and geometrically. And I really want to encourage you to never forget that tiny nudges are at the heart of derivatives. Let's start with a simple function, like f of x equals x squared. What if I asked you its derivative? That is, if you were to look at some value x, like x equals 2, and compare it to a value slightly bigger, just dx bigger, what's the corresponding change in the value of the function, df? And in particular, what's df divided by dx, the rate at which this function is changing per unit change in x? As a first step for intuition, we know that you can think of this ratio df dx as the slope of a tangent line to the graph of x squared. And from that, you can see that the slope generally increases as x increases. At 0, the tangent line is flat, and the slope is 0. At x equals 1, it's something a bit steeper. At x equals 2, it's steeper still. But looking at graphs isn't generally the best way to understand the precise formula for a derivative. For that, it's best to take a more literal look at what x squared actually means. And in this case, let's go ahead and picture a square whose side length is x. If you increase x by some tiny nudge, some little dx, what's the resulting change in the area of that square? That slight change in area is what df means in this context. It's the tiny increase to the value of f of x equals x squared caused by increasing x by that tiny nudge dx. Now you can see that there's 3 new bits of area in this diagram, 2 thin rectangles and a minuscule square. The 2 thin rectangles each have side lengths of x and dx, so they account for 2 times x times dx units of new area. For example, let's say x was 3 and dx was 0.01, then that new area from these 2 thin rectangles would be 2 times 3 times 0.01, which is 0.06, about 6 times the size of dx. That little square there has an area of dx squared, but you should think of that as being really tiny, negligibly tiny. For example, if dx was 0.01, that would be only 0.0001. And keep in mind, I'm drawing dx with a fair bit of width here just so we can actually see it, but always remember, in principle, dx should be thought of as a truly tiny amount. And for those truly tiny amounts, a good rule of thumb is that you can ignore anything that includes a dx raised to a power greater than 1. That is, a tiny change squared is a negligible change. What this leaves us with is that df is just some multiple of dx. And that multiple, 2x, which you could also write as df divided by dx, is the derivative of x squared. For example, if you were starting at x equals 3, then as you slightly increase x, the rate of change in the area per unit change in length added, dx squared over dx, would be 2 times 3, or 6. And if instead you were starting at x equals 5, then the rate of change would be 10 units of area per unit change in x. Let's go ahead and try a different simple function, f of x equals x cubed. This is going to be the geometric view of the stuff that I went through algebraically in the last video. What's nice here is that we can think of x cubed as the volume of an actual cube, whose side lengths are x. And when you increase x by a tiny nudge, a tiny dx, the resulting increase in volume is what I have here in yellow. That represents all the volume in a cube with side lengths x plus dx that's not already in the original cube, the one with side length x. It's nice to think of this new volume as broken up into multiple components, but almost all of it comes from these three square faces. Or, said a little more precisely, as dx approaches 0, those three squares comprise a portion closer and closer to 100% of that new yellow volume. Each of those thin squares has a volume of x squared times dx, the area of the face times that little thickness dx. So in total, this gives us 3x squared dx of volume change. And to be sure, there are other slivers of volume here along the edges and that tiny one in the corner, but all of that volume is going to be proportional to dx squared, or dx cubed, so we can safely ignore them. Again, this is ultimately because they're going to be divided by dx. And if there's still any dx remaining, then those terms aren't going to survive the process of letting dx approach 0. What this means is that the derivative of x cubed, the rate at which x cubed changes per unit change of x, is 3 times x squared. What that means in terms of graphical intuition is that the slope of the graph of x cubed at every single point x is exactly 3x squared. And reasoning about that slope, it should make sense that this derivative is high on the left, and then 0 at the origin, and then high again as you move to the right. But just thinking in terms of the graph would never have landed us on the precise quantity 3x squared. For that, we had to take a much more direct look at what x cubed actually means. Now, in practice, you wouldn't necessarily think of the square every time you're taking the derivative of x squared, nor would you necessarily think of this cube whenever you're taking the derivative of x cubed. Both of them fall under a pretty recognizable pattern for polynomial terms. The derivative of x to the fourth turns out to be 4x cubed, the derivative of x to the fifth is 5x to the fourth, and so on. Abstractly, you'd write this as the derivative of x to the n, for any power n, is n times x to the n minus 1. This right here is what's known in the business as the power rule. In practice, we all quickly just get jaded and think about this symbolically, as the exponent hopping down in front, leaving behind one less than itself, rarely pausing to think about the geometric delights that underlie these derivatives. That's the kind of thing that happens when these tend to fall in the middle of much longer computations. But rather than chalking it all off to symbolic patterns, let's just take a moment and think about why this works for powers beyond just 2 and 3. When you nudge that input x, increasing it slightly to x plus dx, working out the exact value of that nudged output would involve multiplying together these n separate x plus dx terms. The full expansion would be really complicated, but part of the point of derivatives is that most of that complication can be ignored. The first term in your expansion is x to the n. This is analogous to the area of the original square, or the volume of the original cube from our previous examples. For the next terms in the expansion, you can choose mostly x's with a single dx. Since there are n different parentheticals from which you could have chosen that single dx, this gives us n separate terms, all of which include n minus 1 x's times a dx, giving a value of x to the power n minus 1 times dx. This is analogous to how the majority of the new area in the square came from those 2 bars, each with area x times dx, or how the bulk of the new volume in the cube came from those 3 thin squares, each of which had a volume of x squared times dx. There will be many other terms in this expansion, but all of them are just going to be some multiple of dx squared, so we can safely ignore them. And what that means is that all but a negligible portion of the increase in the output comes from n copies of this x to the n minus 1 times dx. That's what it means for the derivative of x to the n to be n times x to the n minus 1. And even though, like I said, in practice you'll find yourself performing this derivative quickly and symbolically, imagining the exponent hopping down to the front, every now and then it's nice to just step back and remember why these rules work. Not just because it's pretty, and not just because it helps remind us that math actually makes sense and isn't just a pile of formulas to memorize, but because it flexes that very important muscle of thinking about derivatives in terms of tiny nudges.